Everyone, I'm Chenhui from the Chinese Academy of Science, and today I'm glad to present our work. And as we know, BGP is the backbone of global internet connectivity. However, BGP was proposed without any built-in mechanisms to ensure security and making it vulnerable to prefix hijacks. And several hijack events have caused widespread consequences, leading to significant financial losses. And to address the vulnerability of BGP, RPKI is standardized by the IETF as a trusted database for BGP. And the core of RPKI relies on resource certificates to delegate IP resources and ROAs to bind an AS to its authorized IP prefixes, and root origin validation, that is RV, to validate BGP routes using validated ROA payloads. And currently, RPKI has proved its effectiveness in preventing major real-world attacks. Before we dive into the detailed problem, let's take a look at ROA and RV. And just a quick note on terminology. A VRP, which stands for validated ROA payload, is simply the verified data extracted from an ROA. So throughout this presentation, you can basically treat VRP and ROA as the same concept. And they both securely bind address blocks to ASNs, and address block, which consists of prefix and max lengths, contains all sub-prefixes with prefix lengths not exceeding max lengths. And for example, an address block shown in this slide covers 3 authorized prefixes. And RV validates validate a route with 3 outcomes. And if no VRP covers the route, it falls into not found state. And if an VRP matches this route for both the authorized prefix length and the ASN is valid. And however, if it's covered by an VRP but violates the length or ASN constraints, and is flagged as invalid, and typically will be discarded to prevent being hijacked. And now we know ROA and ROV. And so how does the router get ROAs? The answer is ROA are delivered to routers via the RPKI data supply chain. And certification authority issues ROA and puts it in a publication point. And then the relying party synchronizes with all publication points and validates the ROA and distributes the VRP to the BGP router. And currently, the latency of the RPKI data supply chain is high, about 15 minutes. And in contrast, BGP convergence occurs within 1 minute. And that means RPKI brings over 15 times operational latency, undermining RPKI security guarantees and impeding network operations. And what's worse, as RPKI adoption grows, the data volume and the number of publication points will increase, and making this issue more severe. According to Merriment, the relying party is a bottleneck. And the relying party, that is RP, it periodically performs validation run. And in a validation run, the relying party works in a wait-for-all sequential order, which is mandated by IETF standard. An RP must synchronize and validate all global RPKI data before it can update its VRP cache and distribute any updates to routers. While this ensures strict routing consistency, it suffers heavily from the struggler effect. And to understand this, we decompose the total latency as the timeline shows. Ready-to-use VRPs are delayed, waiting for the global barrier. And our trace-driven analysis reveals that this blocking latency dominates the total validation run latency. And for reducing the validation run latency, prior works have tried to reduce synchronization or validation workload. However, they accept the monolithic paradigm meaning their performance remains constrained by this waitfall barrier. And so a natural idea is to simply distribute VRP updates immediately and bypassing this barrier. That is a naive pipeline, but there is a fatal flaw. That is, ignoring the dependencies between updates leads to inconsistent RV states and leading to unsafe routing or traffic loss. Here's an example. If we simply distribute VRP-A first, and the route R will be treated as invalid for a while and lead to traffic loss. So the bottleneck is the waitfall barrier, but we can't treat consistency for efficiency by using a naive pipeline. And to break this dilemma, we propose this pipe, a concurrent and conflict-free pipeline. And our approach is to achieve the high performance of pipelining while guaranteeing routing consistency. And to achieve this, we follow a three-step roadmap. First, how do we incrementally calculate VRP updates to feed the pipeline? Instead of generating all VRP updates at the end of validation run, we calculate VRP updates locally per resource certificate. That is our local view update generation. We check the VRP set from the previous and current runs for each RC, and allowing us to generate a local VRP update during the validation run. However, since multiple RCs might authorize the same VRP, simply applying local views to the cache is unsafe, and a global state management is needed. And to maintain global correctness, we introduce a global count. This guarantees that a VRP is only withdrawn from the VRP cache when its reference count drops to 0. And the second step in our roadmap is how to distribute VRP updates in a conflict-free manner. We define two VRP updates as conflicting if their prefixes overlap, meaning they can affect the same route. And our theoretical analysis shows that to maintain routing consistency, conflicting updates must follow strict ordering rules. And our design choice is simple but effective. Rather than a complex ordering scheduler, we use automatic commitment. We group conflicting updates and distribute them simultaneously. This approach is highly practical, and as our measurements show, over 68% of updates are naturally conflict-free, and most conflicts are localized within the same RC. Now, how do we identify these conflicts? And for acquired conflicts between obtained VRP updates is very straightforward. We just detect the prefix overlaps. But the actual challenge is how do we detect conflicts with VRP updates that haven't been obtained yet? And our solution leverages a resource containment environment. That is, no matter how ROA change in the unprocessed certificate subtree, their IP prefixes are strictly bounded by the subtree's root RC's resources. And the key idea is the predictive locking. We use the root RC of unprocessed certificate subtree as a maximum scope to lock potential future VRP updates. And to implement this predictive locking and tracking conflicting VRP updates, we introduce a conflict graph. The graph consists of two types of nodes, VRP nodes and VRP updates nodes representing local view updates, and RC nodes acting as a predictive lock. And then RC to VRP edge predicts future conflicts and acts as a lock. And VRP to VRP edge groups acquired conflicts. Let's see a running example to see how the graph dynamically evolves. Please look at the top half of the slide. And we have an RPKI certificate tree demo. And the circled number 1, 2, 3, and 4 here represent the sequence in which the relying party validates these objects. And in the bottom half, we maintain the conflict graph. And at at the very beginning, the graph is initialized with only the root trust anchor, the RIR node. And now the traversal begins. After step 1, we validate the new ROA1 and immediately insert its corresponding VRP update 1 node into the graph. Then at step 2, the RP validates RC1 and we insert RC1 into the graph as a predictive lock. Because RC1's IP resource scope overlaps with VRP update 1 and edge is built between them. And at this point, the RIR and RC1 nodes act as locks, safely blocking VRP update 1 from being distributed. And next, moving to step 3, the RP discovers another certificate, RC2, and inserts its corresponding node into the graph. But notice what else happened here. The root RI node has been removed. This is our graph contraction because all of the RIR's direct children have now been discovered and inserted. Its internal uncertainty has been completely transferred to its concrete child nodes. Therefore, the RIR node is considered fully explored and is safely removed. And finally, at step 4, we validate ROA2 and generate VRP update 2. And because its prefix overlaps with VRP update 1, and we connect them with VRP to VRP edge. But here is the most crucial part. After step 4 is completed, RC1 has been fully explored and is safely removed. With the RC1 lock gone, VRP update 1 and VRP update 2 now form an isolated connected component. They are safe from any future conflicts and can be distributed simultaneously. And our third roadmap is controlling router overhead. Before jumping into solutions, let's briefly look at RP and router communication. And according to the standard, when the RP has new data, it first notifies the router. And upon receiving this notification, a router typically uses a serial query to fetch only the incremental update deltas from the RP and validate only affected routes. And however, the RP only catches the limited number of the latest deltas. If a router's local state is too old and the required deltas have already been discarded and the serial query fails, the router is then forced to fall back to a heavy reset query, which means it must download the entire VRP snapshot and revalidate all routes again, and it's a very expensive process. Pipelining splits one delta per validation run into many fine-grained deltas, so it brings two parts of overhead. First, overhead from frequent notification. It comes from high-frequency new data notification to routers. And for this part of overhead, we introduce the aggregation interval. We batch updates within a time window into a single notification for balancing data freshness with router CPU load. And the second part of overhead comes from serial query failures. The reason is VRP cache maintains the latest N deltas, and rapidly generating deltas leads to a fallback to heavy reset queries. For this problem, we shift the cache retention policy from delta counting to run tracking, and by maintaining all deltas from the latest N validation run, and rather than a fixed number of deltas, we guarantee a consistent history dips and avoid serial query failure. And for CityPipe implementation, we build the core logic of CityPipe as a reusable library, and we integrated it into two mainstream RPs, routinator and fault. And to unlock pipeline efficiency, we modified fault to the native DFS into a more pipeline-friendly traversal strategy to accelerate the dependency resolution in the conflict graph. Now let's move on to the evaluation. And we evaluated CityPipe across three scenarios. First, a real-world deployment to manual latency and overhead during a live trial. For this, we connected our testbed directly to the live global RPKI ecosystem for over a month. And the second, future deployment scenario to test scalability. Here we use the data-driven generator to simulate future growth. And the third, slow publication points scenario to test robustness against again, we use the generated data. And across all these scenarios, we compared the stock versions of two mainstream RPs, routinator and fault, against their CityPipe integrated versions. Let's look at the real-world deployment result first. And by strictly erasing the structural blocking latency, CityPipe reduced the validation run latency by 73% for routinator, and as shown in the table, while CityPipe introduces a modest increase in RP memory and CPU usage, but it can be easily absorbed by modern server hardware. And more importantly, we observed no statistical change in CPU load on the downstream BGP router, proving that CityPipe doesn't overwhelm the routing plane. And next, we evaluated the future deployment scenario. And under extreme scale, the stock RPs suffers from severe blocking latency. And in contrast, CityPipe eliminates this blocking latency and achieves over 2 hours of latency reduction in the heaviest future workload. And finally, for the robust scenario, as shown in the first two charts, when facing 20 slow non-IR PPs, the baseline degrades up to by up to 6 times due to the waitfall barrier. And however, CityPipe keeps the overall latency low and stable. And furthermore, when dealing with slow IR PPs which contain the root authorities, CityPipe safely delays updates to enforce strict routing consistency. Yet it still outperforms the stock baseline. And to conclude, CityPipe represents a fundamental paradigm shift and is fully compatible with current RPKI infrastructures and can be deployed simply via a relay party software upgrade. And thank you for your time. I'm happy to answer any questions.